Welcome back. Now that you've learned more about working with switches, let's expand your knowledge further by tackling a pesky electrical issue known as switch bounce. In this video, we will talk through what is switch bounce, examples of switch bounce, and then correcting for a switch bounce, also known as debouncing. And then at the end of the video, we'll briefly discuss using a delay in your loop code to save your poor Raspberry Pi system resources. All right, let's get started. When switches are opening or closing, metal plates called contacts must come together or move apart to control the flow of electricity through the switch. If you look at the picture on the left here, you can see those little contacts, or excuse me, on the right, you can see those little contacts between the springs and the push button switches you've worked with. Now, these plates are made of metal, so they will conduct electricity, but this metal-to-metal contact can result in the two plates bouncing off each other a very tiny amount until they settle either fully together or fully apart. This microscopic movement can result in the switch being opened and closed very quickly, typically less than 1 millisecond, until the switch settles into a desired state, and this phenomenon is referred to as switch bounce. All mechanical switches will exhibit some level of switch bounce, but it may not be a problem in their specific application. For example, the light switch in your room has switch contact bounce, but you don't see the light flash on and off multiple times when you flip the switch on. And this is due to the latency or the delay in overhead lighting and most other electronics. The light bulb in your room simply can't turn on and off fast enough for you to see the switch bounce effect. Switch bounce may become a problem depending on how you plan to use the switch input. If the program just turns on an LED based on switch input, then again, like in the case of the light switch, bounce won't really be a problem. Even extremely rapid on-off LED activity will be masked by the amount of time it takes the LED to turn on and off. So the LED will appear to turn on and off smoothly even though switch bounce is still occurring. The problem occurs when you have the ability to check a switch very quickly, like the Raspberry Pi is able to do. We're talking thousands of times a second. So let's think through an example. Imagine you have written a program that is supposed to keep track of how often you drink water each day. Each time you drink a glass of water, you press a push button, and the program keeps track of how many times a switch went from low to high, adding to that count throughout the day. Okay, so pressing the button quickly only one time should result in 1 being added to the current count. But due to switch bounce, there may be a few extra low to high transitions every time the button is pushed. The Raspberry Pi is checking the status so often. These extra contacts of the metal plates as the switch bounces will be logged to the counter even though the actual switch was only pressed once. So pressing the button 8 times throughout the day might result in a final count of 32 glasses of water, which is obviously not correct. Removing these extra counts is called debouncing, which can be done via hardware using additional components or via software. In the interest of keeping electronic connections to the Pi as simple as possible, I'm going to focus this lesson on debouncing using Python code. You may find many effective methods for software debouncing in programs online, but I'm going to walk you through some of the simplest options. One method of debouncing involves checking the input a certain amount of time after the first time an input is triggered. This will allow the time for the metal contacts to stop bouncing or to settle, and the input state can be confirmed once it's steady. This delay is usually not very long, as a delay of around 0.02 seconds should be enough to allow the input to settle into either a steady high or low state. For example, if GPIO 6 was configured as an active low input, the code would look something like this. The first if statement will trigger the very first time GPIO 6 goes low. The program will sleep for 0.02 seconds and then check GPIO 6 again. If GPIO 6 is still false, then 1 will be added to the variable water count. If this second check of GPIO 6 is true, then nothing else will happen and the value of the variable water count will not be changed. Now, there are a couple of problems with this method. If you somehow manage to press the button for less than 0.02 seconds, no water would be recorded, as the second level if statement you see here would not evaluate as false, right? Also, since the entire loop will be evaluated every 0.02 seconds, you can easily end up with multiple water count increments for a single button press, which defeats the purpose of the delay. I think it would take me much longer than 0.02 seconds to push that button. It probably would you as well. All right, so you could increase the amount of delay to avoid multiple water count events being counted when the button is held down. Increasing this delay, however, will increase the amount of time between the first and second checks, which could then allow you a greater chance of pressing the button or releasing it without it being counted. You could tune this value to find a balance between quick presses not registering and longer presses registering more than once, but it may still not give you quite the performance you're looking for. So another method of debouncing includes adding a delay to the loop that runs after an input is triggered. The very first time GPIO 6 goes low, the loop will be triggered. 1 will be added to the water count and the program will sleep for 0.1 seconds before resuming further checks. This will eliminate the possibility of a quick button presses not being counted, and the delay in this loop can be modified to eliminate single button presses registering more than 1 count per press without affecting the responsiveness of the first button press. Okay, so the only problem left with the code we just looked at is that button presses longer than 0.1 seconds will continue to register additional water count events. And this can be fixed by adding a while loop to hold the program as long as GPIO 6 remains low, and you can see that here in the code. The pass command is in the new while loop. It tells that loop to do nothing when triggered, which is exactly what we want. As long as GPIO 6 remains low, the program will remain stuck in this while loop doing nothing and not adding to the water count variable. As soon as GPIO 6 is no longer false, the rest of the initial if statement will run. The final time.sleep at 0.02 was added to debounce the opening of the switch, as without the delay, the bouncing during release of the switch might cause water count to be increased unintentionally. So much work to count your water, isn't it? But it does make for a good example of why we do need these various debouncing methods when we're writing our program, so we can account for all of these different types of scenarios. Okay, so before we move on, let's talk really quick about using a delay to save system resources, because this is actually a really important habit to get into. Due to its tiny size, your Raspberry Pi has a limited amount of processing power that can be devoted to tasks. So this processing power is how much work can be done by the CPU, which remember stands for Central Processing Unit. CPU utilization is a value that indicates how hard the CPU is working. A utilization value of 100% indicates that the CPU cannot handle any more work, and system performance will likely be highly degraded. A low CPU utilization, like a 2%, means that 98% of the CPU is still available and ready to do processing work. Now, the current utilization of the CPU is displayed in the top right corner of the menu bar, and you can see here on the upper right-hand side. In this image, the CPU utilization is at 25%, meaning 25% of the available processing power is being used, with 75% still free. If CPU utilization is too high, no processing power is left over for routine operating system tasks. By running a loop in your program with no delay, you can easily consume more system resources than you really need, causing instability in the Raspberry Pi operating system. If you have a loop checking an input in a program, adding a small delay like 0.1 seconds will free up valuable resources, allowing the operating system to complete all the tasks it needs in the background. Now, your program will likely run no different, right? Because that's a very small delay. However, you'll see a big difference in the CPU utilization number, as well as how much heat is being generated by the Raspberry Pi. And of course, we do not want the Raspberry Pi generating heat. Heat is bad. Okay, before you move on to the activities for this lesson, let's take a few moments and review the concepts we discussed in these two videos. First, we reviewed how hardware can be used to pull GPIO pins up into a default high state or down into a default low state using high-value resistors like we did toward the end of level A. But then in this lesson, we've talked through the basics of how GPIO pins can be pulled up or down via Python code, which simplifies the number of components our circuit requires. We then talked about how slide or toggle switches work, including briefly discussing how you can use these switches to turn power on and off and switch between GPIO pins. In this video, we looked at the pesky problem of switch bounce and specifically how it can cause an inaccurate number of switch presses to be recorded while the metal contact plates of the switch settle into place. Correcting this problem is known as debouncing, and while we walked through that code, you'll get a chance to practice that process too in the activities for this lesson. Okay, and finally we looked at how loops can eat up the Raspberry Pi CPU resources and how adding a delay can address this issue and keep CPU utilization lower, which keeps the Raspberry Pi operating system more stable and reduces the amount of heat the Pi is producing. All right, now that you're familiar with more ways to work with switches and how to correct for switch bounce, go ahead and move on to the activities where you will get to practice these skills. And you'll also get to start adding like a slide switch to your project. So it's a lot of fun.